Okay, for exact equations, first you got to understand the differential of a function of more than one variable. I think I've talked about that. It's all getting blurry. It's been a little while since I did. Okay, so let's just say an f of xy equals x squared e to the negative 2y. Okay? Then the differential, I'm pretty sure I did that in here. Partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. And I think I explained, because I kind of remember now gesturing at the table there. I can't think of what other class I would have done that in. It certainly wouldn't be physics or linear algebra. And it absolutely would have been pre-calculus, so it must have been here. This is just the rate at which the function changes per unit of change of x. And you multiply that by the change in x, and you get how much the slope in the x direction influences f. Okay? And you do the same thing for y. It's like slope in the x direction times a change in x plus the slope in the y direction times a change in y adds up to give you the change in f. It's an approximation just for small dx, dy, df. In the limit, it's exact. Okay, so in this case, partial with respect to x is just 2x. And e to the negative 2y is just treated as a constant. Partial of f with respect to y is this. And I forgot my dx and my dy. Okay? So you just take the derivative of e to the negative 2y, treat x squared as a constant, and that's what you get. Okay? So, now, the equation df equals 0. Has solution f equals c, constant. If f is changing, then its rate of change is going to identically be 0, right? Okay? So the equation x squared e to the negative 2y, that's the equation. The function f, if df equals 0, is going to be a constant. Okay? And should be 1/2, should be negative 1/2. I was thinking that would get absorbed, but it certainly doesn't. Okay? There we have it. And I said E equals, it's Y equals. So there's our solution. We can take initial conditions, evaluate C, and so forth, right? Of course, then the negative natural log of c over x squared is the negative natural log of x squared and all that. You do those manipulations, But I can't go over every possible manipulation, just gotta rely on your knowledge of algebra and calculus, okay? And pre-calculus. Okay, so anyhow, there we have it. Now, the point is, if you know F, and you know that df equals 0, you just set F equal to constant, solve for y, assuming it can be solved, okay? Another way of writing df equals 0 this is df, right? Has that solution because it's the same. Okay? What if you were given this and asked to find the f such that this equals df? Because that's a perfectly good differential equation there. Okay? And of course the equation could also be written dy dx equals 2x e to the negative 2y divided by negative 2x e to the negative 2y, right? And this one would simplify to something really simple, like 1 over x, okay? But if I wrote this out, 2x e to the negative 2y over negative 2x squared e to the negative 2y. And something's not gelling here, but isn't that the solution? Anyhow, okay, you understand that if this function had 2 terms, then this would have 2 terms, and this would have 2 terms, and they might not be separable, they might not be anything that you get a handle on. Okay? So again, the trick comes here. Well, two x e to the negative 2y is the x derivative of f, right? So this is the partial derivative with respect to y of this, okay? Where is it? Negative 2 x squared e to the negative 2y equals a partial f with respect to y. So partial with respect to x of partial f with respect to y equals what? Well, take the x derivative here. You get negative 4 x squared e to the negative 2y, and that's x, that's 4x, okay? And then that's it, because when I wrote this down, it's taking a y derivative, it's really stupid. Okay, you verify this, and you verify this, they're equal. Okay? These have to be equal since the order of partial derivatives doesn't matter. That is, you have f, you do the partial with respect to x, and then you do the partial of that with respect to y. You might as well just do partial of f with respect to y and the partial of that with respect to x. You're doing the two partials. They're independent. Those directions are independent, and I'm waving my hands. It's something you would understand more deeply if you had multivariable calculus. One of the few things here, it kind of relies on a little bit of multivariable calculus, but it's kind of obvious, and we don't try to prove it here. Multivariable calculus will put this in firmer foundation. Okay? Well, that means if you have any equation of the partial of the thing in front of dx with respect to y equals the partial of the thing in front of dy with respect to x, then it comes from one function. And if not, it doesn't. Okay? So I'm not going to ask you to actually solve equations this way, but for homework I'm going to ask you to play around with, I'll give you a function, ask you to do the partials, write out the equation, then pretend that equation is new and test it by taking the partial of this with respect to y, partial of this with respect to x. If they're not equal, you didn't do it right. Okay? Once you have that insight, what we have to do to recover the function, well, that's another story. But it's just simple integration with a little bit of a twist. Okay? I won't even mention what the twist is right now. Your integration constants turn out to be functions of the variable you're integrating with respect to. Okay? Not really constants. There's a reason for that. It's easy to understand that reason, so that's not going to be something that's beyond you. Okay? Okay.